Hello and welcome to Research Matters Podcasts. Today I, Aishwarya Vishwamitra, welcome you to the final part 3, of our series on the research behind the Nobel Prizes in Natural Sciences of the year 2020. In this episode, we discuss the Nobel Prize in Physics. The 2019 winners, James Peebles, Michael Mayer, and Didier Queloz, won the Nobel for their work in discoveries in physical cosmology. This year's research, Nobel laureates takes us on a journey into the galaxy into a strange physical phenomenon, the black hole. The prize was split into two. One half awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity, and the other half jointly to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. To understand the first laureate, Roger Penrose's research, we must travel back to 1915. In 1915, Albert Einstein postulated the theory of general relativity, or, to say it simply, a theory about gravitation. Now, this is what I understand. Gravitation is the force that keeps us bound to Earth, and not floating off into the void. At least, that's how Isaac Newton explained gravity, as a force. But Einstein said that gravitation is not a force, but a curvature of space-time. Could you help me understand this a bit?
So space-time is an abstract concept. It's a mathematical entity. It encodes the idea that things that we used to think as separate. One is space, which is the arena on which things happen, and time, which is this unidirectional thing that we can all feel and experience, should not be separated when we are talking about the laws of physics. When we are describing the way nature works, it should be done taking into account both the space and the time together and not as separate entities. This idea is mathematically represented by space-time. We already have three-dimensional space and one time, and these four now so-called dimensions make up what we now call space-time.
Alright, so what about curvature of space-time? What does that mean?
The curvature of space-time is where things get a little tricky to explain, in words only. I want to put it out there that curvature of space-time does not mean anything that we can imagine directly or see around us. It's an abstract mathematical concept. Having said that, let me try to explain it in simple words. So we know from our lessons in geometry that distances on, let's say, a plane behave a certain way, right? For example, if we know the perpendicular distances between 2 points in two directions, then we can find out the net distance between those 2 points with the help of the Pythagorean theorem. However, it's slightly different in the case when if I take that plane, let's say if I'm writing on a piece of paper that is curved, that is spherical, like the surface of the earth, then what will happen is distances between 2 points will no longer behave the same way as they did before. The formulae will be different, right? Or if you take 3 points like London, Los Angeles, Mumbai, and you know the distances between London and Los Angeles and the other two cities, Mumbai and London, you'll not be able to use Pythagorean theorem directly to calculate the distance between London, Los Angeles and Mumbai. In this abstract mathematical quantity of space-time, distances between 2 points are calculated in a way that is different from the way we used to think earlier, and that is the curvature of space-time. Now, Einstein's way of explanation of gravitation is that gravitation is the reaction of mass and energy to space-time. The theory states that the presence of any mass or energy in space-time affects that space-time and makes it curved. And if there is another piece of mass or energy around which is sitting around in this space-time, then it behaves differently because of that curvature than it would have had there been no curvature. And that is Einstein's explanation. So it goes beyond the idea or the framework of Newtonian physics, where gravitation is this unexplained force for which Newton had given the formula. Einstein is providing an explanation of gravitation via the way the laws of physics play out on space-time. Relativity, first special relativity, then general relativity, are both formulations of the laws of physics playing out on this arena called space-time. And as a result of that, he explains gravitation. So he actually provided an explanation of why we have this phenomenon called gravitation.
Alright, that helps me out. So Einstein's theory met with initial success, right? And other physicists attempted to apply it to black holes?
Physics works with the assumption that one proposes a theory, and then with the help of that theory, other physicists make predictions that can be verified. They use the mathematics of that theory to make predictions on things we see around us. So Einstein's theory, you were right, it met with initial success. That, of course, prompted people, physicists of that time, to make even more predictions which could be either falsified by observations, thus ruling the theory out, probably asking for modifications, or not being able to do that, which would sort of cement the validity of the theory. It would not prove it right, but it would give physicists more confidence in the theory. What are black holes? Scientists took a while to understand that these are objects which are in fact so dense that if any object, anything else, crosses a certain boundary, which you can call the surface for the time being, you will not be able to escape. And by you I mean anything at all, because light, which is the fastest moving object in the universe, could also not escape the pull of gravitation inside, and it would forever stay inside. So people have this idea that they sort of, if things are around, they sort of suck it into them. That's not what it is. Black holes just sit around, but if you throw something into a black hole, it would not be able to escape. Now this is a very drastic idea, right? And physicists were working out the math and trying to understand this phenomena called black hole for quite a while in those decades.
So I guess there was a question mark about the black hole's existence. And in fact, that remained until 10 years after Einstein's death in 1965. Then Roger Penrose came onto the scene. What happened then?
No. Roger Penrose was on the scene for quite a while. So physicists come across this thing called singularity. It means that certain regions or points in space-time where the equations, the laws of nature don't make sense. Now, often it turns out that this is an artifact of the mathematics. Initially, it appeared that black holes and the weirdness of the black holes could be explained away by choosing better coordinate systems and avoiding these singularities which were appearing. So this debate persisted for a while. What Roger Penrose succeeded in doing was to show that black holes are a natural consequence of the theory of general relativity. That the singularity that the mathematics of general relativity predicts in the case of a black hole is not something that one can do away with by doing some clever math. No amount of mumbo jumbo would save the physicist from having black holes. The mathematics predicts black holes and there's no way to get around it. And one Indian called Amol Kumar Raichandani played a very big role here. Lev Landau, a Russian physicist, there was an idea that they had demonstrated which played a big role in the argument that Roger Penrose developed to conclusively show that black holes exist, at least mathematically they exist.
The second half of the prize was awarded jointly to Reinhard Genzel and to Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. So what do you think that supermassive compact object was? Yeah, that's right, a black hole. But how on earth did they find one? Or should I say, how in our galaxy did they find one?
Exactly, you're right. So, finding a black hole would be the real challenge. That was challenging as well as very important. Because if you don't find a black hole, then the theory of relativity, which was so successful, become questionable. The theory itself may not be valid. The mathematical prediction needs to be validated by observations for the theory to hold good. So basically, that is the importance of observing black holes. Why the work of Professors Ghez and Genzel and their groups is important is that they showed conclusively that at the center of the galaxy that we live in, there is one single object whose mass is more than 1,000,000 times the mass of the sun, and it occupies so little amount of space that there is no other explanation of this object than a black hole. Although you cannot observe a black hole directly, what they did is an indirect way of observing this black hole. So the crux of the contribution lies in demonstrating that there is only one thing there at the center. Why I say this is that there was evidence of a lot of mass in that region, but the opinion of physicists or astronomers was divided on whether it's a single object or whether it occupies a lot of space, it's like a diffuse cloud or not. Their observations helped physicists show conclusively that it's a single object which occupies such a small space that black hole is the only logical explanation, this massive object there.
But why did it take 30 years to collect the necessary data?
So it's not that they were artificially taking more time. The reason it took so long is that they were observing particular stars going around the center of the galaxy, and they were observing this whole motion around the center, and they were doing it for quite a few of these stars, and the time scale of these orbits is such that to conclusively demonstrate that these are full orbits, it takes that much time, because the stars themselves take that much time to go around this object, right? So it's not that they were taking time. They were limited by the number of years that it takes to conclusively show that the stars were going around this object at the center. And there's a beautiful demonstration, there's a beautiful video that shows this effect. So, and in astronomical times, this is 20-30 years is almost nothing. Things really happen at the scale of millions of years, if not billions of years. So 20 years is really nothing in that scale. And astronomers, we should remember, were lucky to be able to do this. Things could be different if the conditions, the masses or the mass of the black hole at the center, or the distances of the stars from the center of the black hole was different.
Speaking of time, thank you listeners for spending the last 3 episodes with us, listening to the research behind the Nobel Prizes in natural sciences. Thank you for listening to Research Matters podcasts. For more such science news and podcasts, please log on to www.researchmatters.in.